Hello, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois, and this video is going to take a high-level look at linked lists using the C++ programming language. So by high level, I mean very little code. This is more of a high-level understanding, but there will be some C++ code introduced here. And in future videos, I will go into more details in both making a custom linked list class and also using the standard template library list class. So what is a linked list? It's one of those things like we're moving away from vectors and decks and queues and those kind of data structures into things that are, a little more complicated under the hood. And so a linked list is a set of data structures, and you see there's going to be a class called linked list, and then there's going to be a node class. So it's kind of like they're kind of working together. And so what you see here is for each data structure sitting under the hood, there's a reference to another data structure or a pointer to another data structure. So we say, like, if I have, this is a pointer to the start of my list, and then there'll be data stored in this little location here, and then there'll be a pointer to the next. And then there is another piece of data, and then a pointer to the next, and so forth and so on. And usually we know we're done when we try to go to the next, and we find out there's a null pointer attached. And so, we call this a singly linked list because we can only go one direction, and that's forward. Once you get to here, you can't go back. And once you get to here, you can't go back. And so, there are singly linked lists in the standard template library. There are doubly linked lists in the standard template library. And we're going to talk about the doubly linked list, but they both exist. So they say references / pointers may be addresses or array indices, and it depends on the implementations. But every implementation I've ever seen for a linked list uses pointers to memory addresses because I am dynamically allocating every single element of my linked list as I'm going and adding and pushing and pushing. It's not really pushing, but adding and adding. Every single time I'm adding new memory, I'm not allocating a block of memory like I do for vectors or queues or stacks or anything else. And so what's cool about this here, like everything else, is these data structures, these linkages, and these can be added or removed as I go. So like adding is just think of it. If I wanted to add something between this element here and this element here, well, I would create something and then have this guy point to this one and then this one point to that one. That's kind of how things would go. Or if I wanted to erase this one, I would have to say, okay, this pointer should move over to here and then get rid of this data so that I can come around and point to the new node. So that's kind of where we're going with this kind of thought process. So coming again, just thinking about this linked list versus arrays versus vectors. So we've already done vectors and double-ended queues and all these things to death in previous videos. But like everything else, we do the same behaviors, it's just under the hood things are done differently. Linked lists can grow and shrink as needed. Well, they say like a vector, but the array, as we learned, can't do that because the array is a statically allocated initialized data structure. We know exactly how much space we're going to store under the hood. So fixed size for arrays, but linked lists and vectors are dynamic. That's part of the standard template library. So linked lists can insert a node between other nodes easily, like I was describing earlier. Like it's in a vector, especially if you wanted to add or remove from the start, you'd have to shift everything over, and it takes a lot of time to move everything over one way or the other. But with a linked list, as long as I know exactly where I want to add, it's as simple as just creating some new memory and moving a couple pointers around, and that's all that has to be done. So that's where linked lists kind of shine, in that kind of detail right there. Okay, so as a node itself, we're gonna see that there's a whole data structure that manages nodes. So a node, in this case, since we're talking singly linked list, contains and this is a class, so it's going to contain two completely different pieces of information under the hood. One is going to be the data itself, and we're going to create it like an integer linked list when we create our custom class. But of course, the standard template library lets us create linked lists of any type T. That's what the standard template part of the library is. So the data itself, one or more data fields may be organized as a structure, as an object. And so in our case, it's just going to be a T type or just an integer type. And then again, a pointer. So it's a separate, it's two separate pieces. We'll see the way the C++ code looks here in a couple slides. So the data itself and the pointer, and when we do doubly linked list, there'll be a second pointer that can point me, one in both directions. So that's kind of how things are set up. So a linked list can contain 0 or more nodes, of course, an empty linked list. And so like if I have a pointer to an empty list, it would just point to null pointer. But in this case, there's 3 separate elements here because this does not count. This is just a pointer to the first element, then points to the second, which points to the third, which points to null. So the list pointer points to whatever null, and there's always a null because that's how we know that the linked list has been completed. So we're always going to have to be doing null checks for the work that we're doing. So as I was saying a minute ago here, an empty list is a linked list that contains 0 nodes, and this is exactly what it would look like visually. But of course, this list head pointer would just be null pointer, and it's like null pointer, not just null or anything like that. And that's the simple trivial case, as you could imagine. So here is the definition, or the declaration at least, of what the structure looks like. So you notice it's struct. It could be a class. In this case, just need class with public data, and usually this stuff is kind of all public, and we leave this as a subclass. We'll see this when we do examples later on. But since this is a struct or a class, we're not creating an object of this type. This is just a template for a list node object. So no memory is actually allocated as you're declaring the node itself. And notice in our case, here's an int for the data itself, and then a pointer to the next node. And so we'll see in future videos as well. If we don't make this a pointer, we just make this list node, we're going to actually hit a Stack Overflow trying to define this thing. So that's kind of how we go about it. And we'll see, we'll make this a little more complicated. We'll actually make this a class and make this a little more complex, so make it more complex on the struct side, so we make it easier on the side when we go to write the actual code. So let's see, defining a linked list, and this is not taking into account any of the object-orientedness that we have to think about. This is just setting up, if I just wanted to get something going, I could just say, give me a list node pointer, I'll call it head, and set it equal to null pointer. And there is my empty size 0 linked list. And so the head is pointing to null pointer, and that's pretty much getting something going. This is going to go into the constructor of our custom linked list class, because just setting it up with nothing going on. Okay, so you say null pointer itself. If I wanted to progress through and just basically go through and find and maybe print out every element in my array, or I'm sorry, in my linked list, I would have to start with something like this: linked list node pointer, and then I could say p, and then I would say equals head, or like coming back here, say, because I can have a pointer. Pointers are pointers, right? They're anonymous. They're variables that can point to anonymous data structures. So I could have list node pointer p equals head, and then I could say while p does not equal null pointer, do stuff. And we'll see, would be like, okay, print out p arrow data. And then, so like, can I, I can't add to it, but I'd say like cout p arrow data, and then I could say like p equals p arrow next. And so while we're not hitting a null pointer, we can go to the next node, to the next node, to the next node, to the next node, and so forth and so on. But this is very common code for linked lists, because we can't access the linked list like we can a vector. Like with a vector, we say, get me the 5th element. But we can't do this with a linked list because we have to progress through. All we have access to is the next link, not any random link that, we would have to have pointers to all that. We cannot access this because every element could be anywhere in memory. It's not contiguous like the array, the vector, and all those other kind of things. So the basic operations that we need to perform are very similar to everything that we would talk about in all the other data structures. So I would want to take a linked list. I would want to append to the end of the list. Think of it as like a pushback, right? Like I have a linked list. I want to put a new element as the final element in the list. Then I could also insert a node within the list. We've already shown that. What the tricky part with that is you have to get to the node that you want to insert, and then it's easy. Then it's a It's a very simple operation. And I was just discussing a second ago, maybe if I wanted to traverse the linked list and go through it and print out every element or check to find an element in there or something like that. I could also delete a node, or I could delete the entire list. And of course, when we discuss this using the standard template library, that video, we'll see that there are a lot more operations than just these 5 listed here. So how would I create a new node? So when this kind of thing comes about, it'll be like new node equals new list node. Everything's pointers, right? So since I'm using pointers, nothing is allocated when the program starts up. So it's always, hey, operating system, get me some new memory, get me some new memory, get me some new memory. And again, we're going to make this a little simpler, but if I just set up a new structure, new list node, nothing is initialized. So then I could set up and say, oh, new node's arrow value is equal to num or 9 or something like that. If I wanted to initialize this node that I'm created to some value, I could just go ahead and set this in this manner because it's a structure and it has public access to value and also next or data or whatever it was called. And so in this case, I can also set the next to null pointer. And so this is what everything looks like. This new node is pointing to this newed up memory, and the 23 goes into the one piece of data, and the null pointer goes into the other. So visually, this is what everything looks like under the hood. And of course, it looks much different when you're talking about the reality of what the memory is holding. And so again, this is all just high-level details. We will go into all the nitty-gritties in another video. So appending appending means always put to the end. So I want to add a node to the end of the list. So the basic process would be, I know the start, and that's all I know. I have a pointer to the start. And so what I can do is I can traverse the list to find the last node that's currently in this list, and then I'll new up some memory, and, set everything up I need appropriately, and then take the old last node and have it point to the new last node. So maybe I'm doing things a little differently than what you discuss here, but create a new node, put some data in it. If the list is empty, then we're going to see that we're going to have a little fringe case. How do we know if this is the first element versus any other element? And so if the list is empty, we'll set the head pointer to the node that I just created. Otherwise, I will do as I was just saying, traverse to the end and make sure that this new node gets put in as the new last node. So something like this, if the thing is empty, it just becomes, if this thing was pointing to null a second ago, now it's pointing to this new one. But now something like this, if I want to add a new node, I go, boom, not this one, not this one. This one's the current last one, so I can go ahead and add the new one and take this pointer that pointed to null and now point it to the new null, or the new node. So it's something like this. So, oh, I'm sorry, I didn't realize this was the one I just created. So yeah, a second ago here, this was pointing to null, and this is the node pointer. I need to keep track of this so that everything works out right. Again, details you might not have to worry about later. But this, instead of pointing to null pointer, should point to this new guy. And that's what it does. This points to this one. And now this points to null. And so all these other pointers, new node can fall away, node pointer can fall away, and I'll still have access to everything because I can still get there through the head. I can still get there by linking 3 times over. And everything's done. Everything is appended like it was supposed to. So as we're showing here, we kind of need 2 pointers to make this thing work, at least with a singly linked list. So we need a pointer to locate the node, basically if I'm going to insert anywhere, coming back here, if I wanted to insert here, well, I need the new node, I need a pointer to the new node, and then I also need a pointer to this guy here, because this pointer is going to have to point to the new node, and then this pointer is going to have to go to this node. So it takes a little extra work. Appending is simple because appending to the end means this is a null no matter what, but when I'm adding a node to something in the middle, 2 pointers have to get moved. So the new node is inserted between the nodes pointed at by the pointers. Okay, so so if this is the new node that needs to be inserted, well, this is the previous and this is the one that comes after it, and so the linkages change, right? So this link, if I'm trying to add between these two, this one better go to here, and then this one better go to there. And that's what's happening. This is pointing to here, this one's pointing to there. And again, all these node pointers can fall away and everything is now set up correctly. And that's the weird part of this. You're like, do I need to delete any of these things? Nope. Like you're newing up the data, and the pointers again are just anonymously pointing to various pieces of data, various places in memory, various memory addresses. But at the end of the day, once this is all set up and all the linkages are set in stone and everything is correct, this can fall away, this can fall away, and this can fall away, and we're not going to worry about a memory leak because we have the correct linkages in place. So we are just showing how do I traverse a linked list. Pretty simply, you're just checking for null. Go all the way back to that while loop we were looking at previously. I just say, I'll just take a pointer and I'll point it to the head of the linked list, and then I'll just say, while I'm not pointing to null pointer, do something with the link I'm in, and then go to the next node. Go to the next node. Get to the next node. So as I was just saying, set a pointer to the contents of the head while the pointer that I'm looking at is not null. Do something with that data and go to the next node, and just keep going and keep going and keep going. Okay, so traversing is okay. So like in this case, if I'm starting with whatever this node pointer is pointing to head or list, then it's going to do maybe print the 5. And then do I have this? Nope, it's not doing it. But I'm like, well, okay, now node pointer equals node pointer arrow next. So now it would point to the 13, and I could process the 13, print the 13, and then go to the next. I don't know why there's not an arrow. This is probably just a typo here or something. Go to the 19, print the 19, go to null. Okay, there's nothing left to do since now it is null. So just like inserting, deleting is the same kind of way. I can, as long as I know exactly what node to delete, I can make all the linkages work. I need to know what's previously in front of me, because in a singly linked list, I can never go backwards. So it's a little tricky in a singly linked list to make this happen. And since everything is dynamically allocated, I physically do have to go and actually call a delete on the node that I'm trying to delete. So I can remove a node, I can dynamically delete it, and it requires 2 pointers. One that is the link that needs to be deleted, and one that points to the node before the one. Because again, if I just go ahead and delete this right off the bat, this pointer gets lost, and everything that comes after gets lost, and it's a huge memory leak, and your linked list isn't working properly. So I do need to know the node I want to delete, and I also have to know what's in front of it so that I can say this guy, instead of pointing to 13, needs to point to this guy, which is pointing to 19. So does it show? Yes. So that's what I'm describing here. So I say, okay, previous nodes next now needs to point to node pointers next. And that's what's happening, right? It's coming around, and then I don't have to worry about this before I delete it, because if once I delete this and give it back to the operating system, it all falls away. Node pointer isn't pointing to anything of value anymore. This pointer is not even in use anymore. There's no reason to worry about making this a null pointer or do any of that stuff, any of that sort. So the whole point again is, if I'm deleting this guy, I got to make sure that this pointer gets moved over to the previous node. That's pretty much it, and then delete the memory. And so there you go, delete the memory, and then now everybody's happy. Okay, so then destroying the entire linked list, because again, especially when this thing hits a destructor, you're like, oh, I'm just done with this linked list. You have to absolutely make sure that you delete all the memory you newed up. That's like our #1 rule for preventing memory leaks. So we have to traverse the list, and we have to go through and delete all the memory. So it's a little tricky, and again, we'll see this in a future video. But we have to remove all the nodes, and we have to traverse every node. We have to unlink the nodes and delete all the dynamic memory as we go. And then just to be safe on the end, putting it all back, we should set the head back to null pointer so we don't have any dangling pointers going off to data that will crash our program. Okay, just a little bit more to go here. So there's obviously a linked list template. We will not be templating ours in our custom class, but obviously the standard template library templates the linked list class. So when we're doing something like that, we would specify the type of data. We put that in the angle brackets: int, float, character, skeleton pointer, you name it. That's what we're going to be using for templating, and we can declare the linked list that can hold that data type and that's a definition time, because the templating, remember, we have to generate that code at compile time so that everything works. Generally speaking, we do not dynamically allocate code. Code itself is always created on the spot while the thing is being compiled. So we'll see that next time around. And so variations of a linked list, you will see definitely the singly linked list as we just showed. That is part of the standard template library. There's also a doubly linked list, which is the standard normal list. But what is the difference between singly linked list and doubly linked list? Well, obviously, if you thought about it, what we were just doing, singly linked list only had one pointer, and that went to the node ahead of me. And so now we can have a doubly linked list so that a node can go also just the same as it went to the front, it can go one behind. And so it adds linkages, it adds more complex behavior, but it allows more flexibility, because if I can get to any node, I can't, like I can get to any other node. I can't just go, oh shoot, I fell off, I can't go back. I can always go back. And I don't like this visualization, not that it matters for anything. I like to put the previous node on the left-hand side, but it doesn't much matter where you put things. The data is the data. The previous node takes me to the previous link, and the next node will take me to the next link. And so there's also a circular linked list. So instead of, like in this case, the final node points to null, in this case, the final node points and comes back around and points to the first. And so you're like, like, what is that good for? Well, maybe we'll see, maybe we won't. But it's one of those things. It is, how would you know if you were at the end? How would you know? How would you know you've circled around if you came back around? There's all these little things again that you have to think about if you're going to be creating a linked list of this kind. So, but again, the only real difference is, where does that final link go? Does it go off to the great abyss of null pointer, or does it come around and still point to one of the elements of my linked list? And of course, you can imagine inserting and deleting. There's all sorts of extra logic that goes into making sure that if I'm going to add to the back of the list, that this pointer moves to the correct place, or if I delete something, then all the pointers end up where they need to point to. And so again, this is not this time, this is just the precursor for the next video. But as you can imagine, we've already covered vectors and double-ended queues and stacks and normal queues. And we're also going to take a look at sets and maps and all sorts of other things. And you'll see other data structures throughout your education and your time out in the field. But if you've followed through those videos, when we go to do the list class, you will see there's so many similarities. There are differences, of course. But for now, just understand that the list is part of the standard template library. So a lot of those function calls, a lot of the names like front, back, and end, and push back, and push front, and pop, and these kind of things, they all have most of them are still around. Some of them have been hacked off, because I can't use square brackets and I can't use the at function to get the 9th element like I was discussing earlier. So some of that falls away, but there's new custom stuff. Like there's a new custom sort algorithm for this, because the list is a completely different way of sorting than the other data structures, and so forth and so on. So we will see, if you want to look in the books, table 17.1, or if you want to look online, the Jasudis textbook, or just look up at C++ STL list, you can find all of that behavior. And again, I will describe all that at a future time. So that is pretty much all I wanted to go through. 24 whole minutes of time. Hope you put this on 1.5 speed or something like that. And well, thanks for sticking it out with me. I will see you guys in the next couple videos. Put it all together, write some C++ code one way or another, custom or not. Thanks. Have a good one, guys.